Hello, everybody. Hope you're all doing well. This is a presentation on geysers for Dr. Anderson's volcanology class. This topic was available because it wasn't going to be overviewed in this semester. So I chose it for my video presentation. This presentation is going to be in the form of PowerPoint slides and just a few videos and illustrations. So what my plan is to do is kind of guide us through the PowerPoint slides and videos, and then kind of talk about some illustrations kind of as I'm doing them. So go ahead and get started. So my definition of a geyser, a dynamic subterranean conduit system in which geothermally heated groundwater and steam decompresses and periodically erupts through a vent at Earth's surface. So if you look at this photo, this is Old Faithful, you can see that steam and water are erupting in what appears to be a vent at the surface of the Earth. So they're a rare feature on our planet. There's less than 1,000 globally, and they're typically found in patches of hydrothermal features. So, other hot springs, other geysers, they're kind of found in patches like that. And there can be hundreds of geysers in the same region. Yellowstone National Park houses more than half of all geysers globally. So if you want to see geysers, we're definitely in the right area for that. Another patch of a bunch of them is in Russia, on the Russian peninsula, a little further away. So they're found strictly in regions that are geologically active and where volcanism is common. So their longevity is years to thousands of years, and it's based on several variables. Groundwater, for certain, is a variable. Without it, it would just be a vent. And so by extension, climate is a variable. So an arid region where there's little rain, there's little water to percolate into the ground as groundwater. And so climate does play a role in geysers' longevity. They need geothermal heat too, so that's a big factor. If that geothermal heat is lost, the geyser will die out. They're comprised of subterranean conduits, chambers, and like shafts and stuff, like an underground plumbing system. So without a means to a underground system like that, there'd be no geyser. There'd be no way to house water and steam, and so without that, there wouldn't be anything. And they need access to great depths because that's where the heat is. So depth is important. Depth is important also to build pressure, and these geysers, they also need pressure sealing capabilities. So within the conduit, there needs to be some sort of pressure sealant to allow eruptions to be to the extent of what they are. So, and other things like weathering, and I mentioned climate, but like for example, mudslides that could, flow and roll over geysers, cover them up, cause them to go dormant, extinct even. Those are all factors in a geyser's longevity. So that's all factors for on Earth. Geysers are found on other moons in our solar system. For example, Triton, moon of Neptune, and Io, a moon of Jupiter, has geysers. And the conditions for these extraterrestrial geysers varies from moon to moon, given the different extremes for each of the planetary bodies. And the conditions aren't nearly identical to the formational conditions found on Earth. So let's move on here. Another picture, the same picture of Old Faithful. This is a side-by-side of major volcano locations and geyser locations, just to compare and see that where geysers are found is a geologically active region. And this is indicative of the volcanoes too. So you can see Geyser Iceland here, where kind of the term geyser was originated. Definitely has some geysers and also some volcanism. Yellowstone National Park definitely has geysers. And that area of North America is geologically active. Same in South America. Chile has geysers, we'll see a picture, and is also geologically active. They're in the Andes Mountains. Africa has geysers and geologic activity. The peninsula of Russia, there's a bunch of geysers in kind of the same region there. Also some volcanism. New Zealand, same story, geysers, volcanoes. So geyser eruptions, definitely a characteristic of geysers is their eruptions. Eruptions are spontaneous and varied. No two eruptions are the same, even on the same geyser. So they're all different every time. Eruptions are the result of decompression and thermal to kinetic energy. So kind of what happens, superheated water deep underground and under immense pressure. The pressure is then relieved and the water underground flashes to steam. The steam is more expansive and takes up more volume than water. So steam expands, and as it expands, it rapid rises from the depth. So it can carry with it as it rises, all those minerals and elements that were dissolved in the rhyolite rock, especially silica. And it can also carry with it water that hasn't flashed to steam. So all that is rising up through the center sealed channels, the pressure sealed channels, and it erupts as a vent, or erupts through a vent as a geyser. So these eruptions range in size from small, little kind of bubbling pools that kind of splash every now and then and just kind of get no bigger or whatever, to streams of water and vapor that can be hundreds of meters high. So it's not to say that one geyser only bubbles and one geyser only erupts in columns. It's different every time for every geyser. There are characteristics to each geyser, but overall the eruptions are different every time in their interval ranges. So these eruptions can happen every minute, every month, every year, or even decades long. We saw an eruption for a geyser in Yellowstone recently that hasn't erupted in a very long time, and it's now very active. So, and the eruptions carry with them minerals, especially silica, SiO2, and that deposit of siliceous sinter can be found all around the vents. So there's a video here I'm going to share. This is Old Faithful. So I'm going to switch over to YouTube here. You can see it starting up and progressing. So that's kind of a snapshot of its extent. Got pretty massive, which is kind of exciting. It's a really cool feature. You can see it's spewing out of the vent very fast. And this is all steam and some of it's water, and it's all really, really hot. So the combination of the underground mechanisms at work and then the release here makes for a pretty spectacular eruption. You can see the trees here, how tall they are, and kind of use that as reference for how high this is getting. Definitely hundreds of feet. Old Faithful has the capabilities of doing this every eruption. So this eruption lasts for a couple of minutes, and then like once all the water in the conduit is gone, the eruption is over. So it erupts until all that water is no longer in there. So I got to go back to the PowerPoint. So I'll stop sharing this. Go back to the PowerPoint here. And just take a look at some pictures. This is the steamboat geyser that was dormant for a while. So this photo is like circa 1980, and it's a pretty big eruption. You can see the trees here, and it's even closer. So it's a big one. And this geyser hasn't erupted in a while, but in the past couple of years, it's been pretty active as far as I know. So just the intermittence varies greatly in the eruption. You can even see that this is a little more intense than even Old Faithful. So this is in South America, not as big as the Steamboat Geyser, but just another variation of eruption. This is in Iceland, in that region where the term geyser originated. I think this is one of the more popular ones. And you can see it's, again, just a little different from the other ones. There's actually a video for this one. We'll go ahead and watch, share my YouTube here. So it does this, just kind of steams out for a while, minutes before erupting. There's just no change in the steam, just kind of spewing out. And then really no indication of an eruption until there it is. And that's a huge one. You can see the people here for scale. Then that was a massive eruption. And part of the science of geysers is finding implications to an eruption, and you can see how it can be difficult because there's really no warning signs as far as just observing goes. Usually tools are involved. Go back to the PowerPoint here. All right, that was Iceland. So there's a lot of characteristics of geysers, and one thing that is very important is this stuff called sinter. And sinter derives from silica. So it's a material made of collect silica, and it's basically collected underground in convection-driven subsurface groundwater within rhyolitic rock. So if we go here, you can see the groundwater coming down through the rock. And this is all rich in silica. So it collects in that rock, in that water in that rock, because that water is convecting. So that water's coming down, it's cold up here, and it's coming down as groundwater. And then once it reaches down here, it heats up, and it's under immense pressure, so it stays liquid, and it just kind of circles and convects here. And as it's doing that, it becomes a really good source of dissolving the rock. it's really hot, and that the high temperature makes extracting silica into the water a lot easier. Um, the water is basically superheated. So if you'll read here, superheated water is non-boiling water at or beyond boiling temperatures, and that's what happens when the water is at such great depths and being heated past its boiling point, but the pressure of the surrounding rock is keeping it liquid. So that liquid water is convecting through this rock and extracting silica, so that silica rich groundwater reaches the geyser conduits and chambers where it's deposited and lines the walls as sinter. So it convects and reaches these chambers, and once it reaches these chambers, it deposits that silica rich minerals onto the walls, and that collects as sinter. So sinter acts as a sealant in the chamber, allowing water and steam to escape through a pressure-sealed channel during eruptions. So without the sinter, the pressure coming as this thing erupts, the pressure, if the pressure wasn't sealed from the sinter, it would just dissipate through the rock, and pressure would be lost, and there would be no eruption. The sinter can also be found as a geyserite cone collecting around the spout of a geyser. We'll see a picture of a good example of that. And it's deposited as amorphous opal, so it's non-crystalline. And then it slowly crystallizes over time into quartz. So this is kind of an interesting and unique characteristic of this stuff called sinter, and it's only found near hydrothermal features. So geysers, are kind of the only areas where you find this amorphous opal maturing into quartz. So this maturity over time from opal into a crystalline structure, quartz, can be used to define the age of the geyserite cone, or the geyser in general. So silica is not the only mineral rich in that water. There's other minerals that get deposited after eruptions, and they can become part of these sinter structures, at least what we see on the outside or on the surface. And these other minerals are indications of the types of minerals that were within the underlying rock, and which were harvested during groundwater convection. So the minerals found in these geyserite cones, in let's say this geyserite cone here. So the minerals found there in that sinter, in that geyserite cone, is an indication of the minerals that were in these rocks here, because as this water convects, and it collects silica and other minerals and deposits them here after eruptions. And so we can get a good understanding of what minerals were deposited when this rock was formed. And then that, by extension, is a good implication of the climate that was present when this rock was laid down. So let's go back here. So sinter, just some deposit material found in geyserite conduits and atop here. So this geyserite well, what is it? It's sinter. So geyserite sinter deposit found near Geysers opening. It's kind of the mini volcano shape that, water and stuff comes out of during an eruption. So after each eruption, this cone kind of builds upon itself, and these are called sinter layers. So it kind of gets bigger and bigger and grows in that fashion. And what's kind of unique about these cones is that microbial organisms can attach themselves to the sinter layers that build up on these cones. And they're immobile, so once they get there, they stay there, and they eventually crystallize in the sinter layer that they've attached to as more deposits bring down more sinter and these layers are grown. So that's kind of an interesting thing. These microbial mats is what they're called, are an indication of age and climate too, of when the sinter was deposited. This is a good photo of a geyser cone right here. And you can kind of see it kind of building upon itself with each layer of sinter that forms after each eruption. Castle Geyser, Yellowstone National Park. So let's move on to geyser geometries. The underground geometry is extensive and vast. So it's conduits and chambers descending deep below the surface. Each combination of geyser conduit chamber geometry is unique and has unique effects on the host geyser. So these geometries hold and collect water and superheated water at the deepest depths. So they fill with water, groundwater, and at the deepest depths here, this water is superheated. It's under pressure from the above water, and it won't boil even though it's past its boiling temperature. Because geysers are typically found in groups, many conduits and chambers influence other geysers in the area. So let's say one geyser conduit is filling with water faster, it's going to have a more explosiveness than the geyser that was a little more empty, so by sharing chambers and groundwater sources, they influence each other. They influence the other geysers in the area, with the exception of Old Faithful. From my understanding, Old Faithful is its own individual conduit and water supply, and that's why it is so regular. All the similar hydrothermal features are the result of varying complex subterranean conduit geometries. So we'll see in a second what that can amount to. But some examples of hydrothermal regions could be a mix of geysers and fumaroles, geysers and hot springs, fumaroles and hot springs, a mix of them all. They're all hydrothermal features that kind of intertwine and are connected in that way underground. So this is in New Zealand. This is what is believed the geometry for the Theobald volcanic zone in New Zealand. So you can see there's fumaroles, geysers, hot springs, and other geysers. And then this is Lady Knox Geyser. So you can see how the underground system, these are all kind of intertwined and based off of one chamber, where Old Faithful is not like this. Old Faithful is more like just its own chamber, like here. And I like these diagrams because they show, this one's really good because it shows depth and temperature as you decrease in depth. So down here is basically just magma. I'm kind of getting this ready. So there's typically magma down here, and that's the heat source. And as this water heats up, it's under a lot of pressure from the water above, just putting pressure on it. So it never boils and becomes superheated. And once that water becomes superheated, the water above is cooler, and so and in these chambers, bubble traps can form. And once the cooler water and some of the bubble traps kind of expel out, it relieves a lot of the pressure. And all of this then suddenly decompresses and flashes to steam. And with these pressure sealed walls from the center, they can travel and expel and erupt pretty explosively. This is a good photo of what not to do while viewing geysers. These guys, as you read here, walked onto Old Faithful, apparently took some photos, and were banned from Yellowstone for 5 years and spent 10 days in jail. It's dangerous, and it's definitely not worth it. So there's a final video here I'm going to take us to. It's just a good recap of geysers and their implements and importance.
When you think of a geyser, Yellowstone's Old Faithful probably comes to mind. The famous landmark is known for producing a predictable blast of water and steam every 1 to 2 hours. But not all are so consistent. Every geyser behaves differently, with intervals ranging from minutes to decades, and many are erratic. Scientists study geysers using tools like infrared cameras, temperature and pressure monitors, and tilt meters and seismometers, which measure movement of the Earth caused by steam and water underground. In some cases, researchers have even been able to use heat-tolerant cameras to directly check out a geyser's plumbing. Heat sources deep within the Earth cook the water that moves through these tunnels and cavities. But with so much pressure from water above, the deepest pools can get incredibly hot without boiling. When the pressure eventually starts to release, the water finally boils. The superheated water bursts into a jet of steam and liquid that erupts from the mouth of the geyser. But despite the name of Yellowstone Star, no geyser is eternally faithful. Geysers can be influenced by rain, earthquakes, neighboring geysers, and human harvesting of geothermal energy. Geysers can even die, never to erupt again. Studying how geysers behave can help us understand similar gushing phenomena, both here on Earth and on faraway worlds, and help preserve the powerful spectacles for fans to enjoy. Wow!
Okay, hopefully those were all those videos were smooth for y'all and clear. I wanted to just kind of show my sources here. There's actually not a lot of research involved in geysers, and most of the research done is to compare to volcanic activity. And with that being said, there's still a lot to learn about geysers. I like these cross sections again because they kind of show the dynamics of what's happening underground. All we observe is what happens at the surface, but the interesting stuff to me is what's going on beneath the surface causing these events. So hopefully y'all enjoyed, and we'll see you next time.